Okay, beautiful people, here is your video on the second part of section 8.3. We're going to talk about how to find products and quotients of complex numbers, and then de Moivre's theorem. So the first theorem we're going to talk about is how to find the product of two complex numbers in polar form. And so if I want to do z1 times z2, then I'm going to take their two r's and multiply those together, and then cosine of their two arguments added together. So notice that theta 1 corresponds to z1 and theta 2 corresponds to z2. And whenever I multiply those, I'm going to add those angles to get the result. And then if I'm dividing z1 divided by z2, I'm going to divide r1 by r2, and then I'm going to subtract theta 1 minus theta 2 and theta 1 minus theta 2. Okay, so applying these formulas here in example 1, we want to find z times w and z divided by w, and then leave our answers in polar form. So z times w is going to equal, I'm going to take the r from z and the r from w and multiply them together, so that would be 6 times 8. And then cosine of theta 1, which would be 80, and add it to theta 2, which would be 45. So 80 plus 45 plus I times the sine of the same thing, 80 plus 45. And then I'm just going to simplify that. So 6 times 8 is 48, and then cosine of 125 degrees plus I times the sine of 125 degrees. Okay, when I do z divided by w, then I'm going to use the second formula here, which starts off with r1 divided by r2, so that would be 6 divided by 8. And obviously you can go ahead and simplify that at the very beginning if you want to. You don't have to show this intermediate step. And then cosine of 80 minus 45 plus I times the sine of 80 minus 45. And so that's going to end up being 6 over 8, which is 3/4, multiplied by cosine of 80 minus 45, which is 35 degrees, plus I times the sine of 35 degrees. Okay, next example is very similar. It's just in radians this time, so I'm going to again use my formulas. So z times w, I'm going to take the r of z and the r of w and multiply them together. So that's going to give me 10 times 10. And then multiplied by cosine of pi over 7 plus pi over 10, plus I times the sine of pi over 7 plus pi over 10. And then just simplifying that, that's going to give me 100 cosine of pi over 7 plus pi over 10 is going to be 17 pi over 70. And you could use your calculator to combine those fractions if you're not sure. And then 17 pi over 70 again. Okay, and then when I do z divided by w, that's going to be 10 divided by 10, multiplied by cosine of pi over 7 minus pi over 10, plus I times the sine of pi over 7 minus pi over 10. And so that is going to become 10 divided by 10, which is 1. Cosine of pi over 7 minus pi over 10 is going to be 3 pi over 70, I believe, plus I times the sine of 3 pi over 70. Okay, in example C, we've got to do some work first of getting z and w into polar form. So this is going to be what we talked about last class. So the first thing I'm going to do is convert z into polar form. Okay, and so what I remember is that r is going to equal to the square root of a squared plus b squared. So that'll be 9 squared plus 9 squared. And that'll be square root of 162. And 81 goes into 162 twice, so that's going to end up being 9 square roots of 2. And then to find theta, I'm going to say that sine theta is going to equal to my y over r, which means that sine theta is going to equal to negative 9 over 9 square roots of 2, which is going to reduce to negative 1 over the square root of 2. And so I'm looking for the angle where the sine is negative 1 over the square root of 2, and I recognize that z is in quadrant 4 because it has a positive real part and a negative imaginary part. Okay, so the angle in quadrant 4 that has that sine value is going to be 7 pi divided by 4. Or another way to do that is if you want to do it in degrees, then that would be 315 degrees. So let's go ahead and do this in degrees, and we'll say that it's 315. And if you're not sure about that, then remember, in quadrant 4, I want the reference angle to be 45, and if this is 360, then I know I'm going to subtract. Okay, so in polar form, here's what z is going to equal to. We will have 9 square root of 2 multiplied by cosine of 315 plus I times the sine of 315. Now, I want to do the same thing with w. So if I put w into polar form, I know that r is going to equal to the square root of a squared plus b squared. And so that's going to end up being the square root of 3 plus 1, which of course would be 4, and the square root of 4 is 2. And then to find the theta, I'm going to say that sine theta is equal to y divided by r, and the y is negative 1, and the r is 2. And once again, we have a positive real part for w and a negative imaginary part, so that's going to also be in quadrant 4. And for sine to be a half, I want the reference angle to be 30. So this is going to be here 360, subtract 30, and so that's going to give me a theta of 330 degrees. So in polar form, w is going to equal to 2 cosine of 330 degrees plus I times the sine of 330 degrees. Okay, so now that I've done that, I'm ready to use my formula to get z times w. So z times w is going to be 9 square roots of 2 times 2, and so that's going to give me 18 square root of 2, multiplied by cosine of, and then I'm going to add these angles together. And so if I add those angles together, 315 plus 330 is going to give me 645 degrees plus I times the sine of 645 degrees. Now, anytime we write something in polar form, we want the argument to be between 0 and 360 degrees. And so I need to get that angle 645. I need its coterminal angle so that I can write it between 0 and 360. So what I'm going to do is I'm going to take 645 and I'm going to subtract 360, and that's going to give me 285. And so the final answer that we want to write here for z times w is cosine of 285 plus I times the sine of 285. Okay, and again, the way that I did that is I just took 645 and I subtracted 360 so that I could make my argument be between 0 and 360. Okay, so now when I do z divided by w, I'm going to take the r's and divide them, so that would be 9 square root of 2 over 2, and then cosine of, and then I'm going to subtract these angles, so 315 minus 330 is going to be negative 15 degrees, plus I times the sine of negative 15 degrees. But again, I don't want the angle to be negative. I want it to be between 0 and 360, so I need to take negative 15 and add 360 to it, and that's going to give me 345. So I'm going to write my final answer for z divided by w as 9 square roots of 2 over 2 multiplied by cosine of 345 degrees plus I times the sine of 345 degrees. Okay, the next type of example we're going to look at is using what's called de Moivre's theorem to raise complex numbers to a power. So if you look at this, we have z to the n power. That's going to equal to r to the n power multiplied by cosine of n theta. So whatever that power n is, we're going to multiply our angle by that number for the cosine and the sine part of the complex number. Okay, so in example 2, part A, we have 5 cosine 45 plus I sine 45, and we're going to raise that to the power of 3. And so using our formula, this is going to be 5 to the third multiplied by cosine of 3 times 45 degrees plus I times the sine of 3 times 45 degrees. And so this is going to equal to 125. Cosine of 3 times 45 is 135, plus I times the sine of 135. Now the directions tell me to write in standard form, a plus bi. So I've got to actually keep going here and figure out what this is in a plus bi form. So this is going to be 125, and then I need to figure out what cosine of 135 is. Well, 135 is in quadrant 2, and I know that cosine is negative in quadrant 2. The reference angle for 135 would be 45 degrees, and cosine of 45 degrees is square root of 2 over 2, plus sine of 135 degrees. Well, 135 degrees is in quadrant 2, and sine there is positive, so this is going to stay a positive. And then 135, the reference angle is 45, and sine of 45 is square root of 2 over 2. And then don't forget the I. And then all we need to do to finish that is just distribute the 125. So that'll be negative 125 root 2 over 2 plus 125 root 2 over 2 times I. Okay, in letter B, we're going to do the exact same thing. So we're going to raise this complex number to the 6th power. And so using de Moivre's theorem, that's going to be square root of 3 to the 6th multiplied by cosine of 6 times 35 plus I sine of 6 times 35. Okay, square root of 3 to the 6th power. Well, let's think about this for a second. Square root of 3 is really 3 to the 1/2. So if I raise that to the 6th, 3 to the 1/2, then raised to the 6th power, well, I multiply those exponents, so that's going to become 3 to the 3rd, and so that's going to become 27. And then cosine of 6 times 35, that's going to be 210 degrees, plus I times the sine of 210 degrees. And then I need to know my unit circle. So 27 cosine of 210. 210 is in quadrant 3. Cosine in quadrant 3 is negative because of all-star trig class. The reference angle is 30, and so the cosine of 30 is square root of 3 over 2. And then the sine of 210, 210 is in quadrant 3. Sine is also negative in quadrant 3, so this is going to become minus 1/2 of I, since sine of 30 is a half. And so the final answer here will be negative 27 square root of 3 over 2 minus 27 over 2 times I. Okay, in example C, we're going to have to change the number into polar form before we can use de Moivre's theorem. And so I'm going to do what we've done the last class and then earlier in example 1C, where we change this into polar form. Okay, so I know that R is going to equal to the square root of A squared plus B squared. So that would be 1 squared plus 1 squared, which is going to be square root of 2. And then my sine of theta is going to equal my y divided by my r, which is going to be 1 over the square root of 2. And I know that the number 1 plus I is in quadrant 1 because it has a positive real and imaginary part. And so the angle in quadrant 1 that has a sine theta of 1 over square root of 2 is going to be 45 degrees. And so in polar form, this is going to be the number square root of 2, and then cosine of 45 degrees plus I times the sine of 45 degrees. Okay, so when I raise this number to the third power, which is what we're doing in this problem, if you look back at the original question, we're raising this to the third. This is going to become the square root of 2 cubed times the cosine of 3 times 45 degrees plus I times the sine of 45 degrees. Okay, let's talk a little bit about square root of 2 cubed for a second. So I know that's going to be 2 to the 1/2 cubed. Well, what I can really do is I can switch those exponents and make this 2 cubed to the 1/2, and so that's going to become 8 to the 1/2, which is really the square root of 8. But I need to make sure that I simplify my radicals. So this is now going to become 2 square roots of 2, since 8 is 4 times 2, and the 4 comes out and becomes a 2. So this is now going to say 2 square roots of 2. And then cosine of 3 times 45, which is 135 degrees, plus I times the sine of 135 degrees. And we did 135 degrees back in example A, so you can look back there for the discussion of the fact that cosine of 135 is negative square root of 2 over 2 plus square root of 2 over 2i. And now something really good happens whenever we distribute. So 2 times square root of 2 times square root of 2, the square root of 2's here are going to reduce to be 2, and then times 2 is 4. So this will be negative 4 divided by 2, which comes from the denominator here, and then plus 4 over 2i, since when we distribute this, it's just the exact same thing. And so this reduces to negative 2 plus 2i. And that would be our final answer. All right, the last thing we're going to talk about is how to find the nth roots of a complex number. So how would we find the square root of a complex number, or the cube root, or the fourth root of a complex number? And it's given by this sort of complicated formula. It's not overly complicated, but it sort of looks like it is. And so this is the one formula that I'm not going to ask you to memorize. All of the other formulas from these notes you do need to memorize, but this one I will give to you. I do want to point out one thing about the formula is that this is for radians specifically, but if we were wanting to do it in degrees, we would just need to replace this 2 pi with 360 degrees, and this 2 pi with 360 degrees. Okay, and we're going to primarily work in degrees on this problem, and so that's why I point that out. Okay, and then also on your notes, there was a little bit of a typo. You'll see those money symbols. Disregard that. Just kind of scratch it out, and then you can put what I've written here in its place. And so I'm going to explain how this formula sort of works. But before we do anything else, we're going to have to convert the number into polar form. And so that's doing what we learned how to do last time. And so here I know that r is going to equal to the square root of a squared, 6 square roots of 3 squared, plus b squared, which is 6 squared. Okay, if you go ahead and calculate that number under the radical, it's 144, and the square root of 144 is 12. And then for theta, I'm going to do that sine theta is equal to y over r, so that would be 6 over 12. And so that's going to reduce to a half, and that's going to make my theta equal to 30 degrees. And that's the theta 0 that they're talking about in the formula back up here. So when it says theta 0, we're talking about the 30 degrees here. And so to find the let's back up for just a second. This is the complex cube roots. And so cube would imply that n is equal to 3. That means there are going to be 3 cube roots of this complex number, and we're going to start with k is equal to 0. All right, so this is going to be z sub k, and I'm going to try to do red anytime I do k, so you can see where that's coming from. So z sub 0 is going to equal to the nth root of r. Well, n is 3, and r is 12, so that's going to be cube root of 12. And then cosine of, and I'm just following along with the formula here, theta 0 divided by n. So theta 0 was 30, and n is 3, so that's going to end up being 10, 30 divided by 3, plus 360 divided by n. Well, 360 divided by 3 is 120 degrees, and then multiplied by k, which in this case is 0. And then I'm going to have plus I times sine of the same thing. 10 degrees plus 120 degrees multiplied by k, which for this one is 0. Okay, once I simplify those numbers inside the parentheses, I'm done with z sub 0. So cube root of 12 multiplied by cosine of 10 degrees plus I times the sine of 10 degrees, since 120 times 0 just cancels out. Okay, now I'm going to do z sub 1. And this is again going to be the nth root, which is 3, of 12. And this time I'm going to have cosine of 10 degrees plus 120 degrees multiplied by k, which in this case is now 1, plus I times the sine of 10 degrees plus 120 degrees multiplied by 1, since in this case k is 1. And so that's going to equal to the cube root of 12, and then cosine of 10 plus 120 times 1 is 130 degrees, plus I times the sine of 130 degrees. Okay, and then finally I'm ready for z sub 2, and that's going to be the last value of k, because if you look back up here at the definition, the last k value is always n minus 1, and in this case n is equal to 3, so 3 minus 1 is 2. This is going to be the last cube root of this imaginary number. Okay, so we're going to have here, once again, cube root of 12 multiplied by cosine of 10 degrees plus 120 degrees multiplied by 2 this time, plus I times the sine of 10 degrees plus 120 degrees multiplied by k, which is 2. And so this is going to equal to cube root of 12. I'm just going to simplify those numbers in the parentheses. 2 times 120 is 240, plus 10 is going to be 250, plus I times the sine of 250 degrees. Okay, so our answers here, I'll try to highlight them for you so that you can kind of see what we're talking about as far as the answers go. The answers are going to be right here. So z sub 0 is here. That would be our first answer. Z sub 1 is here. That would be our second cube root. And then our third cube root is down here at the bottom. All right, in example B, we want to find the complex fourth roots of negative 4i. So the fact that we're finding the fourth roots tells me that n is equal to 4. And the first thing I want to do is convert negative 4i to polar form. Well, this one is more easily done just by plotting it. So if this is the real axis and this is the imaginary axis, then negative 4i is going to be down here. That's going to give me a radius of 4 and an angle of 270 degrees, since that's the angle that that point is sitting on. So in polar form, this is going to be 4 times cosine of 270 degrees plus I times the sine of 270 degrees. Okay, so now what we're going to do is we're going to find our general formula only this time for the complex fourth roots of negative 4i. So what that means when I say general form is I'm just going to do z sub k and then write one formula that would represent all of the fourth roots. Okay, so this is going to be the fourth root of 4, and then cosine of theta 0 divided by n. So that's going to be 270 divided by n, which is 4, plus 360 divided by 4 multiplied by k, plus I times the sine of the same thing, 270 divided by 4 plus 360 divided by 4 times k. And this is going to be for k equaling to, starting at 0, going to 1, and then to 2, and then to 3. Okay, and I need to put that at the end so I can tell the person looking at this how many of these complex roots there are going to be. And so since there are going to be 4 of them, the k values are going to be 0, 1, 2, and 3. Now, I'm going to simplify all of this, and I'm going to start with the fourth root of 4, and I'm going to do this kind of off to the side. So the fourth root of 4 is the same thing as 4 to the 1/4. Well, that's the same thing as 4 to the 1/2 raised to the 1/2, and 4 to the 1/2 is 2, and so that becomes 2 to the 1/2, or the square root of 2. So the fourth root of 4 is just the same thing as square root of 2, multiplied by cosine of 270 divided by 4 is going to be 67.5 degrees, plus 360 divided by 4 is going to be 90 degrees times k, plus I times the sine of the same thing, 67.5 degrees, sorry about the extra degree sign in there, plus 90 degrees k, and that again is for k is equal to 0, 1, 2, and 3. Okay, last example, we want to find the complex fourth roots of w is equal to 1, and we're again going to write it just in general form like we did in example B. And so again, since I'm finding the complex fourth roots, that tells me that n is going to equal to 4. Okay, so let's go ahead and figure out what the angle is here. So w equals to 1, you can think about that as 1 plus 0i. So 1 plus 0i, if this is the real and this is the imaginary axis, then that's just going to be right here. And so the radius is going to be 1, and the theta is going to be 0 degrees. Okay, so z sub k is going to equal to the fourth root of 1 times the cosine of theta 0, well that's just 0 divided by n, which is 4, plus 360 divided by 4 times k, plus I times the sine of the same thing, 0 divided by 4 plus 360 divided by 4k. And then k is going to take on the values, since this is the complex fourth roots, it'll take on the values 0, 1, 2, and 3. Okay, so the last thing I'm going to do is just simplify all of this. The fourth root of 1 is just 1. And then cosine of 0 divided by 4 is 0 degrees. And obviously I don't need to write that, but the online homework is going to have you fill in a box with that number. And so the number that you would fill into that box for this particular problem would be 0, so that's why I'm writing it here. Okay, and then 360 divided by 4 is 90 degrees times k, and that's for k is equal to 0, 1, 2, and 3. Okay, you guys let me know if you have any questions, and that'll do it for section 8.3.